Welcome to the second video on GPUs. So in this video, we will study the CUDA 10 language and figure out how to program GPUs. So we'll mainly be confined to the software interface. So the CUDA language was introduced way back in 2006, 2007. CUDA stands for Compute Unified Device Architecture, which was NVIDIA's CUDA toolkit. It was primarily designed as an extension of C++ because C++ used to be the most popular language those days. And even if this were to be done now, C++ would not be a bad choice because a lot of pointers are used in GPU programming. So that is where the use of C++ is required. So this allows the user to write codes, especially for GPUs. And again, this is primarily an NVIDIA GPU language. So the GPU component of the FAT binary, which we have discussed in a previous lecture, just to recap, a FAT binary has both CPU code as well as GPU code. So the GPU component is compiled into a virtual instruction set called PTX. PTX is basically a RISC-like instruction set, and it just assumes that there are an infinite number of registers. So one advantage of this is that, let's say if there is a piece of code, and clearly there's a lot of intellectual property in the piece of code, we don't want to release the piece of code, right? So what we would like to do is we would like to compile it to an intermediate language such that the original code is not recoverable, and then we release, right? So then what we do is we release the piece of code such that users can run them. But the point is that there are different kinds of GPUs with different sizes, right? So there are GPUs, small GPUs, bigger GPUs, less cores, more cores, and so on. So there's a need for dynamic recompilation. So dynamically, let's say at runtime, we have a JIT compiler. JIT means just in time, which means that whenever there is a requirement, the code is compiled, and it is compiled to a binary known as shader assembly or SAS. So this is specific to a GPU. So every GPU has its own low-level instruction set, which is SAS. So the dynamic PTS to SAS conversion happens at runtime. So CUDA has a dedicated compiler called NVCC. So you can think of NVCC kind of released on the same lines as GCC. So NVCC basically compiles the CPU code and the GPU code. All right. So it produces a FAT binary, which contains both the CPU code as well as the GPU code. It has both. So here is the flow of the compilation of a typical CUDA program. So we create a .cu file. So the .cu file is sent in both directions, towards the C compiler and towards the CPU compiler and towards the GPU compiler. So let's look at the CPU side first. So we have the regular compilation stages. So we have the C++ preprocessor over here. So the C++ preprocessor creates a file with this extension .cpp4.ii. Then we have a regular C++ compiler called CUDA FE++, which extracts the C++ code. And we will see that here there's a connection with the GPU, so we will come back to it. But basically what happens is that in the C++ code, it will generate kind of special code. The reason is that a lot of the C++ code, what that would do is that would invoke a function within the GPU and get back its results. So the way that CUDA works is that we have a regular C++ program, which is the entry point. Then what we do is that we invoke a function within the GPU. Right, so we transfer data first to the GPU, then we invoke a function within the GPU, and then we come back. All right. So after executing something on the GPU, we come back, and then we get the data back. So this is the typical process. So what is done is that when the user is writing the code, The user simply writes C++ code for the CPU and the GPU, but all of this internal plumbing, which means set up the arguments, set up the data, actually call the function on the GPU, which involves many low-level calls, and again get the data back. So all of this code also has to be injected automatically into the C++ code. So that is what this file stands for. And also, of course, a bunch of files are generated. So it's important to understand what is a stub function. A stub function basically means that if, let's say, in the C++ code, I'm calling a function to be run in the GPU, then instead of calling the real function, which I cannot because it's written in a separate ISA and so on, I actually call a stub function. The job of the stub function is to do a bunch of things for me. So these include setting up the arguments, right? Then basically set the state of the GPU, essentially initialize the GPU, send the arguments to it, say that a new function will execute. So there are a lot of commands which need to be sent to the GPU to just initialize it. Then basically execute the function, right? So all of these things are managed by the stub function. And this is kind of library code, API code, which is automatically generated. And once that is done, then the C++ compiler compiles the program and we generate a .or object file. On the same lines, if we go to the GPU side, again we have a preprocessor. And as we know, a preprocessor's job is just to replace macros, right? Is just to replace the contents of macros. Then we have the compiler CICC, which takes the C++ code that is to be executed on a GPU and converts it to PTX. Then the PTX code, we have a PTX assembler. So the PTX assembler basically runs, so this is something which typically runs at runtime. No, I'm sorry, I stand corrected. So the PTX assembler's job is to take the PTX instructions and kind of generate the machine code, which is PTX machine code, and generate a .qbin file, which is essentially a GPU binary file. But of course, the ISA is PTX. So then the object file and the PTX, they are combined into what we have been calling a fat binary. And along with that, once the GPU code has been generated, references to it via stub functions are passed to the C++ code such that it can link to the GPU functions. It knows how to call them, right? And all the additional internal plumbing, that's what we call in programming language parlance, is automatically added. So the key point is that there are two parts. There is the C++ compilation part, which primarily incorporates the effect of stub functions. And there is a GPU part, where what we do is that we take the pre-processed macros, generate PTX binaries, and combine both into a fat binary. And that is kind of what is distributed, right? So these dotted lines are kind of references which we have discussed. So once a fat binary is generated, we are ready to execute it. When we execute it, the runtime will basically figure out what to run on the CPU, what to run on the GPU. And furthermore, some JIT compilation is done to convert from PTX to SAS and do many GPU specific optimizations. These are very important. Many of these GPU specific optimizations have to be done. So now let us come to the code that runs on the GPU. So we'll gradually work on this example and keep on expanding it. So the aim over here is to define a function that will execute on the GPU. A function that executes on the GPU is known as a kernel, right? So this is known as a GPU kernel. It's a basic function that is executed on the GPU. If there are n GPU threads, n versions of the kernel are run. All right. So basically, this is something that is meant to execute in parallel. So think of it as a parallel function. So I'm showing the example code to add two arrays. So let's look at this step by step, piece by piece. So whenever we have the identifier underscore underscore global underscore underscore, this basically refers to a directive which tells the CUDA compiler that this is basically a kernel and this is supposed to execute within the GPU, and that too in parallel. So the name of my function is varchar and it doesn't return anything. So it takes 3 floating point arrays as input, A, B, and C. So these are pointers. So these are pointers to which memory space we will discuss that later. But if it's running in the GPU, think of it as a pointer to the GPU memory space, right? But all of this will be described later in a reasonable amount of detail. So what we do over here is that, let's say in this case, we are arranging all the threads in a one-dimensional axis. So let's say if there are n threads. So we are assuming a simple case where there are n threads and each of these arrays have n elements. That's the simplest case, right? So we are assuming that all the n threads are conceptually arranged or numbered along a single x-axis, and each of them has a number from 0 to n minus 1. So this is a standard technique that is used in almost all parallel programming, where every thread has a number. So in almost all other frameworks, every thread has a unidimensional number, but in the case of GPUs, every thread is assigned a multidimensional number or ID. So we are first looking at the unidimensional case where the ID can be between 0 and n minus 1. So in this case, what we do is we get the ID of the thread by reading the variable thread idx.x. So I have already indicated to you that we can have a multidimensional ID for a thread, which means that there could be 3 components, x, y, and z. So we'll maximum go till 3 dimensions. So in this case, we don't have any y and z component. So we'll see, in a couple of minutes how that is ensured. But let's assume we have no y and z components. We only have the x component. So the x component varies from 0 to n minus 1. So every thread gets its number. And once it does that, it just does the addition that is assigned to it, because what is the task? The task is to take 2 arrays and add them element by element. So if this is the problem of adding 2 arrays element by element, we simply take the index, all right, and we find the relevant index, right? So we find a idx, the value from the idx index for A. Similarly for B, we add them and assign them to the corresponding entry for C. See, if the array has, let's say, 1,000 elements and we run 1,000 such threads in parallel, then of course we are done. So as we have discussed, the global directive makes it run on the GPU, and the rest we have discussed in fair detail. So as I discussed in the last slide, threads, GPU threads, have an arrangement. So if we want, we can arrange them linearly on a single axis, as we just saw in the last slide. We can have a two-dimensional arrangement where every thread will have an x coordinate and a y coordinate. Or we could have a 3D arrangement where the threads could have a x, y, and z coordinate. So all these 3 arrangements are possible with their advantages. But an advantage is that, look, if we are working on volumes, right? So let's say we are looking at an airplane wing, which is a volume. Then this arrangement kind of naturally makes sense. If you're working on a 2D plane, like solving the heat equation on a 2D plane, then maybe this arrangement makes sense. And for a simple example of adding 2 arrays, this arrangement makes more sense. So what we have done is that here we create this arrangement is a thread block. So we have a 1D, 2D, and 3D organization for a thread block. And thread blocks themselves can be arranged in a 1D, 2D, or 3D fashion. So that is known as a grid. So where did we go? We had a thread. Threads are grouped into what are called thread blocks. And thread blocks are again arranged in a grid. So again, for thread blocks, we have 1D, 2D, and 3D. For a grid, we have the same thing, 1D, 2D, and 3D. Same thing, exactly the same thing. Threads have two types of coordinates. So the first coordinate is the coordinate of the thread within the thread block, and the second coordinate is the coordinate of the thread block within the grid. Right? So thread within the block and block within the grid. So if you can think about it, the universal coordinate of a thread is actually 6 numbers. So first x, y, and z is the coordinate within the thread block, and the second x dash, y dash, z dash is the coordinate of the thread block within the grid. So now let's come to the coordinates of a thread once again. Right, so this is an important concept, and this is where the CUDA language differed somewhat significantly from its predecessors, which were traditional parallel programming languages such as OpenMPI and OpenMP and MPI. So, which is that every thread was assigned at least a 3D coordinate within its thread block. And of course, we may choose to ignore a few of these coordinates, in a sense, set them to 0. For example, in our array addition example, x and y were set to 0. They kind of defaulted to 0. Likewise, we can have a 2D organization, so this is possible to do. In a 1D arrangement, our thread was fetching thread idx.x, but it could have also fetched thread index thread idx.y or z as well. The addition, needless to say, is happening in parallel, and this is where the power of the GPU comes, in the sense we create a lot of threads, and the GPU does a fantastic job in scheduling and managing them. So let us now look at a 2D thread block, and we will add some more code. Right, so we have kind of been stingy in showing our code, but in this case we will add a little bit more code and show you more of it. Right, so in this case we will consider a 2D thread block. So the two coordinates are idx and jdx. Idx is the x coordinate and jdx is the y coordinate. So what we are doing, so we will discuss the main function later. So incidentally, now we have also gone into the C++ part, but we'll discuss that later. So let's again take a look at the kernel, which is this part. So in the kernel, we have the underscore global directive, which again tells you that it's a GPU kernel. All right. Then we have matrix addition. So in this case, what we want to do is we want to take two 2D matrices, and we want to add the 2D matrices. Okay, so we want to do a matrix addition of both of them. So let's say we want to add matrix A and matrix B and produce matrix C. So since we are arranging the threads in a 2D block, and for the sake of simplicity, let us assume that there are n cross n threads. The size of the thread block is n cross n, and the size of the matrix is also n cross n. Well, then there is no problem. We get the x coordinate, we get the y coordinate. So we read thread idx.x, thread idx.y. And then what we do is we just add corresponding elements of both the matrices, similar to what we had done for arrays. So as you can see, it is A idx jdx, B idx jdx. We add them and we get C idx jdx. As simple as that. So of course, in this case, we have n square parallel threads, and they are transparently managed by the GPU. So of course, you can argue that there are limits to the number of threads. In fact, there are. So there is a limit to the number of threads you can have in a thread block, but n can be very large. Of course, that is fine, but then for a large n, that's not a problem. We can take a large matrix and kind of break it into small tiles and assign each tile to a thread. So that is easy to do. Now let's come to the main function. We are seeing the C++ part first. So the dot 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 indicates the code that we are not showing. So gradually these dot dot dots will start opening up. But let's take a look at some data structures at this point. So we want to create a data structure that will tell us the threads per block. So we will define a variable threads per block. This is of type dim3. Dim3 means dimension 3, which means at the most it can contain 3 numbers, even though it is not restricted to, it's not limited to containing only 3 numbers. It can contain 1, 2, or 3 numbers. So the number that is not initialized will default to 0. So in this case, the z coordinate is defaulting to 0. That's the reason we are passing only 2 arguments, right? And so the argument that's not passed is assumed, that axis is assumed to not exist. So you're passing 2 arguments, which means n coordinates on the x-axis, n coordinates on the y-axis, so total n square threads. So this is of object dim3, and of course it has many constructors. We can take a single argument. This would mean just n threads on the x-axis. N comma n would mean n threads on the x-axis. I mean n cross n threads basically on x and y-axis. And n would mean n cube threads, x, y, and z axis. So now what we do is we invoke the mat add kernel over here. And invoking the kernel has a special syntax. So to highlight the special syntax, I will erase all the ink on the slide. So we will have these 2 markers. Kindly pay great attention to these 2 markers. So these markers are essentially indicating the configuration in which we are executing. So the first is the structure for the arrangement of thread blocks within a grid. If this is 1, it means that look, there is only 1 thread block per grid, so you need not bother. No problem. And the second one is the data structure that we just initialized, which is this one, which is saying we have n cross n threads per thread block. So a single thread block with an n cross n arrangement. So this arrangement is very important, and this is how the GPU initializes the kernels and the threads. Once that has been passed, then we send the arguments. So the arguments in this case, well, the CPU basically has to pass pointers to GPU memory. We will see that that is possible to do, but we have not shown the code. But the code is coming. But the important take-home point over here is that you need to understand that the arrangement has to be specified within the 3 less thans and 3 greater thans. The first is the arrangement of thread blocks per grid, which in this case is defaulting to 1, and threads per block. Right? And we are creating basically an n cross n matrix. Okay? And 1 block per grid. Let us now look at a 2D matrix of threads and 2D matrix of blocks. So we will look at something quite similar. So we will start with the main initialization, the main function. Again, we are not showing the code over here. So we will define 2 data structures, 2 dim3 data structures. The first one is the dimensions of the grid. Because in this case, what we want to do is we want to arrange the thread blocks themselves in a grid, and we want to do it in a 2D grid. So we will have n by 16, where n is a parameter that we have defined earlier, right, within these 3 dots. So the dimensions of the grid are n by 16 cross n by 16. So we have n square by 16 square thread blocks within the 2-dimensional grid. So this goes as the first parameter to the kernel invocation. So as you can see, the kernel is over here. Its name is mat_add. And the first parameter to mat_add that is going is actually the dimensions of the grid. After that, we define the arrangement of the blocks within the thread block. So the threads per block are arranged as 16 cross 16. So we have 16 cross 16 threads per block. So if you actually look at it, it's a 2-dimensional 16 cross 16 structure. And there are n by 16 such structures, and again n by 16 such structures. So the total is still n square. But in this case, we have divided it in a different manner. We have arranged them first as separate tiles, kind of think about this, as separate thread blocks within a grid. And within each thread block, of course, they are arranged in a square fashion. So with this, we give two dimensions, two DIM3 data structures, no defaults over here, and the three arrays A, B, and C. So it is interesting to see how this information is processed within the MATAD kernel. So within the kernel, we compute two indices, IDX and JDX, but IDX is of course computed in a special way. The same holds for JDX as well. So to understand, let us draw the grid in a better fashion. Each of these squares here is a thread block. So what we do is that we first take a look at this parameter, which is the block dim.x, is a block dimension. So it essentially says that what is the size of a thread block in its x-axis. So the block dim.x is basically this quantity over here. Okay, so it is basically this quantity over here. So if let's say the block index is 2, then this would be the first block, this would be the second block, this would be the second, sorry, 0th block, first block, and second block. So the block index is 2. What we do is we multiply 2 times block dim.x, which is exactly what you see here. Block idx.x times block dim.x. So we multiply 2 times the block dimensions, right? And so then we get the starting point of this. And then we add the thread index.x, which is this quantity over here. So this quantity over here is the thread idx.x. Okay. So this quantity here is the thread index. And so this is how we get the x coordinate. We are assuming the x-axis goes this way. So this is how we are getting the x coordinate of the thread, which is exactly, this point, right? So the x coordinate is coming how? We take the block dimension, multiply with the block index, of course, the x coordinates of them, and we add the thread index. So this is how we exactly come here. And let's say the actual thread is over here. We do the same. This time we go down the y-axis. We are assuming the origin is over here, and again these are numbers 0, 1, 2, 3, and so on. So we do the same for y also. We multiply with the yth component of the block index, multiplied with the block dimensions, and then what we do is that we arrive at the starting, and then this displacement, right? This displacement is thread idx.y. Okay, so this displacement over here that you are seeing is thread idx.y. So that is how we get the coordinates of this thread over here on the grid, which is basically idx and jdx. Okay, so the computation of the coordinates of the thread is slightly more difficult over here as compared to what we have seen earlier. But that's okay, because in this case we have a hierarchical organization. We are organizing or arranging threads within a block, and we are also arranging blocks within a grid. So because of that, we have this two-level thing, right? And so what we are doing now is that we simply take the components of A and we take the components of B, and we add them. And the moment we add them, we get the equivalent component of C. All right. So this is CUDA programming in all of its glory. So of course, here we have considered a 2D matrix of threads and a 2D matrix of blocks. So we could always make it 3D and 3D. So this would slightly become, this would become slightly complicated, but to a certain extent, that's okay, right? So we will then know what is to be done. So what we will do in that case is that we will also have to take care of the third component, which is also the z-axis, we'll have a similar formula and we can work out. So then if you have so many threads, how do they operate, right? So how are they synchronized? So that is an important question. Because the point is that, if let's say that this is a small computation, in a large computation, we would want all the threads to arrive at a barrier, which is basically a common point. So all the threads arrive over here. And once all the threads have arrived over here, so here you can see one thread is fast, it has arrived quickly, but the other threads are lagging. But once all of them arrive at the barrier, all of them can be released at once and they can go. So this ensures that if a thread is over here, it has some information about the rest of the threads that they have actually crossed the barrier. So the barrier can be thought of as a rendezvous or a synchronization point. And all the threads must reach it before any of the other threads can proceed. And there is a CUDA function called the sync threads __ sync threads function. So in fact, you will find a lot of CUDA functions with __ sync threads. And so this can be used to implement a barrier. All right. So the idea over here is that thread blocks are meant to execute completely independently. So the way that we take a computation is that, of course, we divide the entire computation as a grid. We divide the grid, as we have seen, into thread blocks. Each thread block is meant to be completely independent of the other thread blocks. So most of the functions of CUDA, sharing, synchronization, most of them, of course, there are global ones which hold for the entire grid, but most of them hold within a thread block, because the idea is that a thread block works independently of other thread blocks. And within a thread block, you do as much of fine-grained synchronization as you want, right? So this has key implications with the hardware, and because that's the way the hardware will schedule threads. So an interesting divergence is due here. So the way I'm recording this video is that I'm using Camtasia Studio. And so then I record the raw video, but when the final video is produced, it actually uses my NVIDIA GPU. And the NVIDIA GPU's usage, you can see the entire laptop like becoming really hot. And the GPU is used, the usage is between 80 and 90%. But if I don't use a GPU, it actually takes hours. The reason that this completes so soon is only because of my GPU. All right, so after that, we reconverge here. So we have discussed the computation part to a large extent. Of course, we have not discussed most of the nitty-gritties, but at least the basic idea has been provided. Now let us look at the memories. So GPUs have many types of memories. So we have been primarily looking at the device memory. So again, note these underscores at the beginning and end. So this is a constant feature, it will be a recurring theme of the CUDA language. So the device here, memory, means it resides in the GPU or the device. The constant means it resides in the GPU's constant caches. Shared means it resides in shared memory. So shared memory is something that is there per block, which is per thread block. We assign some memory which is shared only by the threads within a thread block. This is also within the GPU. All three of these are within a GPU. We have managed. So the managed is an interesting memory. So it's not really high performance memory space. All of these are memory spaces. But of course, this memory space is both a virtual space and a physical space, but both are within a GPU. The managed is a space, both virtual, right? And it has a physical connotation, but let's look at it from the programmer's point of view. This is shared between the CPU and GPU in the sense a GPU pointer can be used to access CPU memory and vice versa, as long as it's there within the managed space. So you can think of this as kind of like a shared memory between CPU and GPU. So there's a general flow of computation where we transfer data from the CPU to GPU, right? Perform the computation on the GPU, and the results come back. So let us now look at the full code for vector addition. So we have already seen the kernel over here where we take the arrays and we add them. So given the fact that I've seen this, I'm not discussing this. But in the main function, I will still have these three dots, but I will still have, I'll show you more. So what we can do is that let us first initialize the arrays A, B, and C on the CPU. So these are floating point arrays with n entries. So we just use three malloc calls and then we initialize them and we have three arrays A, B, and C. So mind you, they are in the CPU's memory space. I'm sorry, CPU memory space. Then we initialize the arrays. Right, so sorry, I'll just erase the ink here. So we allocate memory on the CPU, we initialize the arrays. Now here is the fun part. The fun begins here that we allocate memory on the GPU and we get a pointer which is as such useless on the CPU. But it is essentially pointed in the GPU's memory space. So instead of the malloc function, we use the CUDA malloc function. The CUDA malloc function that we have over here, what that basically does is that it allocates an array on the GPU. Okay, and so basically it's again of type float star and the size is specified over here. So recall that we computed the size over here. So we create three such arrays on the GPU. And once these arrays are there on the GPU, we get the pointers, but of course, as I said, they're useless on the CPU, but they can be used to copy these vectors from the host to the device. What is the host? The CPU, the device is the GPU. So what we do is that we do a mem copy. So we first give the GPU pointer, then the CPU pointer. We then provide this flag, right? To which function? To the CUDA memcopy function, whose job is to transfer data between the CPU and GPU. We provide this flag CUDA memcopy host to device, which computes data like which copies data like this. And then we launch the kernel. We have already seen this, right? Previously, this entire part was under dot dot dot. So now we provide the pointers, which are the GPU pointers. Of course, they can't be the CPU pointers. So we had done a little bit of cheating over there. So now we are not doing it, I promise. So now we are sending the GPU pointers to the arrays and we are launching the kernel. Once the kernel is done, it will finish its execution. So this is the only GPU part and this is what exactly the stub function will refer to in the compilation process. Finally, we transfer from the device to the host. No problem, we do that. So from the device, we transfer it back to the host. So which means the host, the CPU, has the contents in the array C. Then we free space on the GPU. So we do CUDA free GA, GB, and GC, which basically, so whenever we have a malloc, we should be doing a free. This is good programming practice. And we do that in the sense we free the three arrays on the GPU, GA, GB, and GC. All right, so just a quick recap, allocate memory on the GPU, copy the inputs, run the computation, free the memory. So what we have seen is that there are three phases in every computation, which is that we transfer data to the GPU, perform the computation on the GPU, and transfer the results back to the CPU. So you think about it, this transfer time over here is kind of a waste in the sense that we are not doing any active computation. So the solution is that we create different streams of computation and we overlap them in time such that at least the GPU can be used. So what we can do is instead of transferring all the data at once, we transfer small chunks of the data and then we perform a computation on them. At the same time, in a pipeline fashion, we transfer the next chunk, right? So instead of transferring all the data, we pipeline the computation. So of course we can't do pipelining at the level of bytes. So what we do is that we have a bigger granularity. We create a stream as a queue of work items. Operations in the same stream are executed in program model. However, operations across streams may overlap, so there is no synchronization across streams per se. So what I want to say is clearly visible over here. Let's say that this is the original computation. So in the original computation, we transfer data to the GPU. All right. We do the computation, it goes back to the CPU. So instead of that, let's do one thing. Let's transfer half the data to the GPU. And then let's do the computation. At the same time, we transfer the other half. So you can clearly see the overlap here. Then we transfer the results back to the CPU. At the same time, the computation happens for the second stream. So this is stream 1, this is stream 2. And then we transfer it back to the CPU. So what we can see is that because of the higher degree of overlap, instead of 3 time units, it takes 2 time units. So we have a straightforward speed up of 1/3, right? So this is quite amazing because we didn't do anything. All that we did is we divided each of these into like 50%. Okay. And what we basically did is that after dividing them into 50%, we achieved an overlap. All right. So once we achieved an overlap, we were able to reduce idleness or wastage of time. And this was done by having two streams, right? By having two separate streams, this was achieved. So this is an illustration of parallelism with streams. Needless to say, streams are a method for improving the performance. I'll now show you the CUDA code for streams. But of course, I'll not go to the level of detail that I went in the previous case. But you can refer to NVIDIA's official documentation shown here. In fact, the code is from theirs. The code is not mine. Okay, I'm not claiming originality for this. The code is theirs, and I, in good faith, am explaining it. So, how do we create streams? Well, that's simple. So we have this CUDA stream underscore T type. So kindly note this nomenclature that NVIDIA is using. So every consecutive word, let's say CUDA starts with a small c, but then S starts with a capital letter, and underscore T denotes a type. So CUDA stream T is a stream type. So we create two streams. Then what we do is that we have a for loop. Doesn't go very far, just two. So we create two streams. And also what we do is that we create two floating point arrays. And sorry, we create one. We create one floating point array and we just do a CUDA malloc on the host. Now what we do is that for both the streams, if you can see the for loop, this goes from 0 to 2, which is for both the streams. We do a CUDA mem copy async. So CUDA mem copy async is just an asynchronous memory copy, which means that this is not tied to other actions. So this is essentially what gives the streams the independence. So I'm not showing the rest of the code because the rest of the code is shown over here. But basically what I'm trying to tell you is that we are doing a mem copy from the host to the device. So this is the device pointer. And the offset on the device pointer is I times size. So initially I is 0, so this is just going into device pointer. So recall that we have the host pointer, we have already mallocked it, and its size is 2 times size. So the first chunk gets transferred like this. The first set of size bytes get transferred from the host to the device. But of course, in this case, the operation of transferring data from the host to the device is assigned to stream I, right? So stream I initially will be 0 and 1, but let's call it stream I. So this is a part of the stream. So as you can see over here, these transfer operations have to be explicitly assigned to streams. So this is being done right at the time of function invocation, that we are saying that look, you transfer it, but transfer it as a part of this stream. Then what we do is we invoke the kernel, and in the kernel it's just a simple one-dimensional kernel, but what we are doing is that we are also assigning the kernel to a stream. So every call basically is getting the stream ID along with it. And then of course we are sending other arguments which are specific to the kernel. So we are not worried about that. But the important point is that the kernel function is taking the stream ID as an argument. I'll slightly reduce the clutter, and then what we have over here is again we have a copy, which is the copy from the device to the host. And again, as you can see, we have the host pointer and the output device pointer. But the most important thing is that even this operation is being assigned to the stream over here. So we are assigning all three operations to this stream, and these are not synchronous in the sense that they are not tying up the GPU. And it is just that we are telling the stream that look, these are the three operations you need to perform. Within the stream, as you have seen, as we have just defined over here, that operations in the same stream have a program order, which means that within the stream we'll have a program order. But across streams, of course, we can relax the order. So this is captured by the async directive over here. Let us now introduce an even more elaborate construct known as a CUDA graph. So what we realize is that the cost of launching the kernel and performing the data transfers is high. That's the reason it's a good idea to divide, let's say, large tasks into smaller ones and schedule them. So if there are a large number of kernels, we group them into streams, which did give us some benefits, but that is sadly not good enough, right? We can do better. So an alternative solution, particularly if you have a large number of tasks with a fair amount of heterogeneity, is to use a CUDA graph. So this will be used or is typically used to specify the nature of the data transfer, the details of all the kernels and the dependencies between them. So we basically specify everything the same way we did in a stream. But of course, a stream is like a linked list and a graph is more like a DAG or a directed acyclic graph. So then we have an automatic engine which does all of this, that validates the graph, pre-computes a schedule for it, schedules all the activities in the GPU, on the GPU. And if let's say there is a dependency between one task and the next, then needless to say, the first task executes first and the dependent task executes after it. So unlike program order, we have a task dependence order, and that is respected. It does more. It's way more intelligent than that. So basically it adds code to prefetch data. So when the previous task is running, some code is added to prefetch the data for the next task. And of course, allocate resources, particularly if we have multiple such graphs running or multiple applications running, as is possible in modern GPUs, that we schedule resources appropriately. Visualization of a graph, well, we can have a graph like this, each of them is a task, and each node, in fact, can be a subgraph on its own. It can be a subgraph. So an arrow from A to B indicates that A executes first and B executes later, right? So an arrow from, let's say, task A to task B indicates the dependence. So more about CUDA graphs. Well, CUDA graphs can have all kinds of events. So we can have different kinds of nodes. So we can have kernels, of course. Along with kernels, which are GPU functions, we can also have CPU functions. We can wait or record an event. So what is an event? I'll discuss in the next slide. But an event is basically something like a timing event or something like a performance counter, where we say that, look, start recording the time from this point and end over here. So we can understand how long an execution took. Then, of course, signaling a semaphore. So signaling a semaphore is basically a signaling mechanism where it's a more sophisticated version of locks and unlocks, where the idea is that if one thread is kind of waiting here on a lock, another thread can come here, it can signal it to unlock, and this thread will start. So that is signaling a semaphore. So of course, locks can have two states, locked and unlocked, but a semaphore can have multiple states. So it is a generalization of a lock, where a lock is called a binary semaphore. But semaphores need not be binary. For example, we can have a counting semaphore, where let's say anytime we signal it, we increment it, anytime we wait on it, we decrement it. And we always want that the count of the semaphore will be more than one to release a thread. So this is an OS concept, but this can be looked at. So you can think of this as a generalization of a lock. And of course, a node can contain another subgraph. So these are the main functions that we have. CUDA graph create, see the same naming scheme, add kernel node. Similarly, we can add other kinds of nodes and add dependencies. So we can add dependencies between all of these nodes. So that will create a complex graph. And as we have discussed, it is a hierarchical recursive structure where one graph can be subsumed within a node. It is also possible to create a graph out of a stream. So this is known as stream capture functionality, where we take an existing stream and we create a graph out of it. Then we get the additional advantages of a graph. But given the fact that a graph is a heavyweight thing, in the sense that a lot of additional code, including prefetching and validation, etc., is added along with a graph, it is typically preferred when we have a fair amount of computation, which is reasonably heterogeneous and unstructured. Right, so finally, as we had promised, we come to events. So CUDA programs have to be profiled for performance. So we need to insert events in the code, find the time between elapsed events. So that will tell us, for example, how long a kernel took, or how long, let's say, a piece of code took. So we have the CUDA event elapsed time function. So then this will tell you how long it took. So I'll explain with an example. So let's say we have this function CUDA event create, where the start event is created. And similarly, we have another event that we create called stop. We create these two events, start and stop, and we pass their pointers. We start recording. So we start the timer for the start event. And of course, this can be associated with the stream ID. So for that stream, we start recording. The computation keeps going. Then we again record one more event, which is called stop. And so, of course, again for that stream ID. So at this point, what happens is that we need to synchronize, which basically means wait until all the work associated with the event stop is completed. So what can happen is that the event itself, processing the event, is a multi-stage operation. And so we would at least want that all the work associated with the stop event, which is recording exactly at what point the stream is at, that completes. So that is why we call the synchronize function, which is highly recommended if you want to get an accurate time, which is also capturing a point in the stream, a relevant point in the stream. And then all that we can do is that we can call the function CUDA event elapsed time between the start and stop functions. So that will be stored in the variable etime. Etime is for elapsed time. So that will tell us between the start and stop functions, which captures all of this computation, how much time did it take. This information is basically profiling information which can be used by programmers and application developers to tune and make their code more efficient. Good. So we have finished the video on programming GPGPUs. So we have completed the first two parts. We have a reasonably good understanding of the CUDA 10 language. So as we speak in 2021, the latest version of CUDA is CUDA 11. That viewers are most welcome to look at. In the next video, we'll look at the design aspect of GPGPUs, in the sense how are the GPGPUs designed, right? And what are the design choices? And also look at the design of popular NVIDIA GPUs in this space.